The next session will be also not easy, I guess. It will be about quantum physics, but I hope it will be as interesting and lively as the last one on mathematics. So we have two talks, and this time it will be talks on experiments. The first by Dr. Vedral from Oxford, and the second by Dr. Briggs, also from Oxford. Please, we start. They decided to talk from above in order to see the audience more. So please.
Yes, I always talk standing up, actually, so I think this is the natural state of affairs for me. I hope you're comfortable with that yourself. This is a talk about quantum physics. I'm a quantum physicist, and I'm not religious, actually. I thought I should come clean, simply because it's very difficult to tell that with physicists in general, whether we are or not, and that's because most of us feel closer to God than anyone else, actually. This year's Nobel Prize comes from my discipline, quantum optics, and these are guys who can take a single photon, put it inside a small cavity, and then integrate it with a single atom with 99.99% precision. So anyone who can do this surely has got to feel very close to God at that level. Now, of course, having said that, and I think this was mentioned many times here, there is a humbling thing behind it as well. Namely, it's taken these guys 20 years plus to get to that stage where they can manipulate nature at that level. So it's very hard, you know, we find it difficult to even do that. Imagine now adding more atoms and so on. So I'm guessing when someone does this with 100 or 1,000 atoms, there will be another couple of Nobel Prizes in physics. That's going to take another 20 years. That's how difficult it is. So of course, we fully understand as physicists how little we know, even though we may work at this very deep level. This is going to be a joint work with my postdoc, Mile Gu here. He's probably the person that I want to advertise more. Carolina Wiesner is from the University of Bristol. Elizabeth Reaper is a former PhD student of mine. And this was actually work completed just before she completed her PhD. The slides are all from Mile. I'm actually very bad. I always use whiteboard when I lecture. And I know students love it. But now this was just the easy option for me. I just simply borrowed these slides from him. And so anything fancy you see is really due to him. And he's extremely creative. This guy is worth advertising. He's actually already going to a permanent job in a couple of months' time. He's decided only to publish in Nature, by the way, this year. He's got 4 Nature papers. I don't know how he does it, but that's basically it. What I want to talk about is something, this is probably not the mainstream research in that sense, and I think that's why we are lucky to have people like Templeton and a few other private investors who actually see the value of research that goes maybe beyond 3 standard deviations from whatever is the norm. And I thought this topic was actually appropriate for this meeting. So the question will be really a novel way of thinking about the arrow of time. I thought it was the appropriate topic because we physicists find it fascinating that none of our microscopic laws, in this case quantum laws, they contain absolutely no asymmetry in time. Everything works just as well backwards in time as it does forwards in time. And yet, everything we see around us in the world only goes in one direction. And you can argue probably that our deepest human emotions come from the fact that, in fact, certain things or many things will never happen again. You know, they're here now, but they won't be here tomorrow. So it's a topic we all feel is a very deep and important topic for us. But like I said, for physicists, it's also important for a different reason, and that's because we really can't derive this. Boltzmann was probably the key person who struggled a lot, and he offered a few ways, but they're all really fudges. I think I'm cutting corners, and I'm probably being unfair to 100 years of research on this, but basically we don't really know how to do that properly in physics. And here is one way, and I thought it might be fun for you to look at that. So here is Occam's razor, and Occam's razor will have to do with complexity. I will define it, of course, in a strict sense of that word. This is one of X number of spellings of Occam, I think. There are at least 3 I know of, but I think there are probably more. And of course, the famous statements there is that you should really work with a minimum number of assumptions, and you should discard anything that's on top of it. There's a slide probably you can't see here, which offers Occam's version, and then it says Occam's professor, and it says something like this: when faced with 2 possible ways of doing something, the more complicated one is the one your professor will most likely ask you to do. I don't know if Miller was sending me any subliminal messages here, or maybe more direct messages, but I think that's kind of his version of that. Of course, every scientist you can probably think of, every glamorous scientist you can think of, they have their own versions of Occam's razor. Of course, there is one attributed to Newton, there is the famous statement by Einstein, and so on. And all of them boil down to this simple fact. Now, of course, I'm going to talk about it in a formal, speaking in terms of simplicity and saying you should just take the simplest explanation, of course, requires you to define what you mean by simple. And different humans obviously disagree about this notion, and that's something I'm going to avoid. Being a scientist, I will have a strict definition, and it's going to be really, really mind-numbingly simple, because I can't work with anything more complicated than that. It's going to be ridiculously simple. But then I can prove some formal statements with that, and that definition will actually appeal to physicists quite a lot. So here is this, graphics capturing Occam's logic, in the sense that if you have something with more assumptions, but it explains exactly the same thing, it has the same outcome, if you like, as something with fewer assumptions, then you should keep this logic with fewer assumptions. For me, the number of assumptions will actually be the complexity of something, which I will quantify with entropy. I mean, these are probably details you don't need to worry about if you don't know what they are. But effectively, what's that going to become is the capacity of your computer to store information. That's going to be the simple thing in my talk. And here is, I think Mila is very fond of these movies. So he would present it in a way that, suppose you're the Matrix programmer and you want to recreate certain kind of reality and fool everyone else into thinking that that's the way it is in this world. Then, of course, what you really want to optimize in the first case is the size of your disk, the memory that needs to hold this kind of simulation. There's much more than that, obviously. You might want to optimize the amount of energy. You might want to optimize the number of steps you have to make and so on. But like I said, I've got to keep it simple, because otherwise I can't really prove anything with this. It becomes very, very complicated. So I'm only going to be talking about the memory of this disk. And you'll see the connection with the arrow of time, and it's another very beautiful idea. So here is the formal statement, and I think it appeals to everyone in physics very much. You observe all sorts of processes around you in nature. So this is going to be this really simple model of how we view making models and theories of reality. You have something that I really simplify to a bit string. So each of these x's can be either 0 or 1, because we know that we can reduce everything ultimately to that. And I observe a certain process that spits out zeros and ones. So I keep making measurement. Once I get a 0, once I get a 1. And I see a sequence of these things up to the present point. The present point is the one where I want to start recreating this kind of sequence myself. So I observe it for a little while. I kind of learn about the properties, the statistics, and so on. And then I ask myself, what is the smallest computer that can actually recreate the future of this kind of process based on what I understand the future should look like given the past? That's going to be the task that we are faced with. And I'll give you the punchline, actually, just not to keep you waiting. What's interesting is that if you do this quantum mechanically, then you're in general much more effective than if you do this classically. So quantum mechanics, in some sense, if you follow Occam's razor, is the right way of compressing your observations in the real world. Note that I never put quantum mechanics into it in the first place. These are classical bits, and I have some classical random process, and I'm not even making any assumption. Thank you. I'm not even making any assumption as to how this sequence is generated. I'm not being dogmatic about it in any way. All I want to do is make a machine that's able to reproduce the same kind of output later. And that's the task. And the entropy, just for those of you for whom this means anything, will be the usual entropy that we use in information theory. Anyway, the brute force approach is that I literally record all possible sequences in the past, and then for each of these sequences, I have a future sequence that I have to generate. Now, obviously, if you're talking about even tossing a coin, something as simple as that, I have to record 2 to the power of n exponentially many historical sequences in order to talk about the future, and that becomes exponentially ineffective. So the question is there a better way? And there is a better way. So what you do is you look at all of these sequences which give you exactly the same future behavior, the same future statistics. And what that means is that you don't have to memorize them, if you like. You don't have to encode them individually, separately. You can just think of them as one unit in your memory, since they are indistinguishable as far as the future behavior is concerned. And so you can discard anything else. You can only keep those pasts which will really lead to a definitely distinct statistics in the future. It's as simple as that. I think it's all very natural and simple. And so you break the whole past, if you like, into causal sets. And all of these guys in the causal set effectively require you just one bit of information, if you like. And you can really ignore any other complexity. This leads to a concept of an epsilon machine. An epsilon machine is the machine that keeps these causal sets and uses the causal sets to generate future. And then you talk about the entropy of these epsilon machines, and this is your complexity of this process. Note that it's very different to other kinds of complexity. So some of you may have heard of Kolmogorov complexity. Kolmogorov complexity tells you that the most complex process is a random process. This guy says a random process is the simplest process. I actually don't need to remember anything about the past. All I need is a coin, and I need to toss a coin. That's super easy. I don't need any memory of anything in the past. That's what it means to be random. It doesn't affect anything in the future. And this definition appeals to us physicists much more. So complexity, according to this logic, lies somewhere between complete randomness and complete order. If I have a sequence of zeros only, that also requires absolutely no memory on my behalf. But somewhere in between these two lies what this measure would identify as complex behavior. As one of the key players, a guy called Crutchfield, some of you may know him from the Santa Fe Institute. And he wrote a PRL, among few other people actually, introducing the notion of epsilon machines and this kind of complexity. And then he proved a few things about these things. It's a huge field. This slide is just there to impress you regarding the number of applications that these epsilon machines have had. That's nothing else. I'm not trying to communicate any other information. Other than this result that he proved, saying that no classical system can simulate a given stochastic process better, if you like, using less information than the epsilon machine. He said, here is the best you can do. You can't go beyond this kind of compression. And it's going to be my first punchline, that quantum mechanics does better, does always better, more or less, than classical. You can compress more. You're closer to being most efficient, whatever this may mean. And that's probably now the topic that I want to touch on. In fact, before I say that, what Crutchfield did was to speculate on the relationship between the next quantity that I will introduce and this capacity that he introduced. And that's going to be the key thing now to focus on. Ask yourself, what is the absolute minimum of information, going now beyond epsilon machines, that a past of a process needs to generate its future? Okay? How much information is there in the past encoded about the future behavior? And interestingly enough, you wouldn't be probably surprised to know that there are people who thought about it, and there is a measure called mutual information by a guy called Shannon. And this mutual information really looks at the overlap between the past and the future, statistically speaking. And you can quantify the overlap. It's another entropic quantity. And this, in a way, says, here is how much nature needs from the past in order to generate the future behavior. So this is the absolute minimum. Whatever you do in terms of, even if you go beyond epsilon machines, you take quantum mechanics, you take whatever is your favorite theory, you cannot go beyond the bare minimum. One interesting thing to note here is that this quantity is completely symmetric with respect to reversing past and future. So basically, the amount of information you need to generate the future from the past is exactly the same as going backwards in time. This is what I said was one of those things that we physicists have a problem with. Why does nature seem completely symmetric with respect to this interchange at the microscopic level, whereas we don't really see that at the macroscopic level? Now, people like Crutchfield and another guy, Grasberger, if you choose to read only one paper on this, read this guy. This is a fantastic paper, Randomness, Information and Complexity, picked up by the editor of Nature at that time, the famous John Maddox, who actually wrote a really nice news and views about this stuff, because it was a genuinely novel approach to complexity. Crutchfield said, maybe the discrepancy between our model, the fact that when we make a model, we are never as efficient as nature, maybe that's what's at the root of irreversibility. So the fact that when we engage in dialogue with nature, we try to reproduce natural behavior, our entropy is always higher than the best that nature does. Maybe that's at the root of all the irreversibility and the second law of thermodynamics and the increase in entropy. It's a really novel idea, and I think it's an interesting one. And that kind of justifies the arrow of time title. And in fact, here is that way, that's kind of a graphical way of representing the capacity you need to simulate this, and the capacity nature itself, God, metaphorically speaking, uses to run the process here. And it's interesting that they're different. And in fact, I think Crutchfield wrote another paper, Time's Barbed Arrow, to talk exactly about this simulation and the discrepancy being at the root of that. Now, of course, me being a quantum physicist, I want to show you that quantum physics can do better. And this is what's interesting in this. And then I will make a couple of speculations, and then I will give you a break, I suppose, after that. So why can quantum physics make a better compression of information? The key is going to come from those pasts that kind of are fuzzy, namely those paths that have a little bit of overlap, but they don't completely overlap. Remember, if they completely overlap, then I can discard one of them. I don't need to keep both of them. But if they have a little bit of overlap, you would think that you could discard something, but classically speaking, you still have to keep both of them, and that's what leads to inefficiency. We've already heard that quantum logic is a little bit fuzzy. Sorry, I'm being extremely vague now because I know I'm addressing at most two other quantum physicists and everyone else is not in the audience. But basically in quantum mechanics, you can have states that are completely different to one another, and yet they are indistinguishable, not completely distinguishable, if you like. And that's going to be the key, how we can squeeze in more and get exactly the same kind of future predictions. So there is a formal slide about it. I don't want to bore you too much. I'll just give you the example, and I think you'll get the gist. So in quantum mechanics, these are these probabilities to go from the past to the future. But in quantum mechanics, we'll really be using these amplitudes as they are known, and somehow we'll be entangling the past events with the future events, and that's going to be the game there. So let me show you a really simple example. The gist of it, as proven here, will be that quantum complexity here is really smaller than classical. So here is an example. Imagine you have a coin, which could be either in a state 0 or 1. So you have this coin in a box, you perturb it a little bit. And then the rule is simply that if the coin is in the state 0, if it's heads, then you generate heads with some probability 1 minus p, and you flip it with probability p. It's very simple. It's really like tossing a coin with uneven probabilities. However, if your coin is in the state 1, then you do exactly the same but with inverted probabilities. So you send something with probability p to a state 0, and basically this coin to the state 0 with probability 1 with probability 1 minus p. So basically, it's important to know whether you have 0 or 1, because the probabilities to get into 0 or 1 in the future are slightly different. but they are not completely different. They still have an overlap because in both cases you can have either 0 or 1, and that's exactly the case I was talking about before. Classically, you still need 1 bit of information in the now, in the present, because you need to keep track of whether your past was state 0 or state 1. You can't get away from that. And that's 1 bit of information. You have to keep the value 0 or 1. Quantumly, and that's really the punchline, you can in fact, I think this summarizes more or less what I've been saying, you can in fact use superpositions of zeros and ones. I think more or less everyone has heard the buzzword, and you're using these amplitudes which reflect the probabilities p and 1 minus p. And the whole point is that these two states are not completely distinguishable, and therefore when you put them together, they require less, I mean, depending on the probabilities, they require less entropy. And in fact, this graph, and I think that's probably the main thing to look at, shows you how much less you can do. So here is the amount of information in bits. Here is the probability p going between 0 and 1. So classically, you always have to use 1 bit of information, unless p and 1 minus p are the same, unless it's a genuinely random process, in which case I said you don't need any information whatsoever. So here is the classical result. Here is the quantum result, much better, obviously. It agrees at this maximal point as well. And then the absolute best, which is what nature itself does, the mutual information I mentioned, is given here. So you can see that quantum mechanics comes very close to it. Now, of course, I want to make the two speculations that in fact, incidentally, if you're wondering, by making good timing, I think, by making more and more complex scenarios, you can make this closer, and you can make the gap become arbitrarily big between quantum and classical, if you like. Now, the two interesting things are the following ones. So basically, of course, there are always questions of whether this kind of logic is used by natural systems. I think that's an exciting question for us, because natural systems, of course, are in the game of predicting the future given the past. There's also a technological question there about wasting as little heat as you process information. And what's interesting, and that's the point I'm going to make now, the arrow of time, according to this logic, still doesn't disappear with quantum mechanics. So even if you do quantum encoding and quantum processing, you are still not saturating the natural bound. So that's interesting. There's a question of why. Why is quantum mechanics not as efficient as that? Of course, there are all sorts of experimental realizations that we are thinking about. The final slide is really this speculation that I think is very appropriate for this audience, and it addresses exactly this question of efficiency. So I'm going to flip it around. One way of talking about this is that there is still this arrow of time in quantum mechanics. The other way of talking about this is that this might show us that quantum mechanics is maybe not the last word as far as our understanding of nature is. Maybe this gap points to another theory which is now going to be so efficient that the simulation of nature according to this theory will be as costly as nature does it on its own. So basically something without any friction in that sense. I think this is a great speculation. I think it's a really nice idea, but I have no idea how to even begin to go in that direction of something that could be more effective. So as usual, you know, we are simpleton physicists, and I think this is very difficult for us. Anyway, I hope you have a rough idea of what this is all about. Thank you for your attention.